Hi folks, my name is Brian Ferlito and I'm here to talk about a lung adenocarcinoma data set. So this data set was uploaded to cBioportal from Nature in 2008. It was by a study that was entitled Somatic Mutations Affect Key Pathways in Lung Adenocarcinoma. This data set had multiple files. I took two. The first one is median RNA-seq expression data, and the second one is clinical patient information that has been scrubbed of all HIPAA-violating identifiers. So what I want to do with this data is I want to predict prognosis and whether the patient lives or dies. So the first thing I do is I dive deep into the first file, which is the gene expression data. There are 20,000 genes. That's a lot of genes. I don't want to train my model on that many features, so I want to reduce that number. So what I end up doing is I read the paper. There are 26 statistically significant genes that are determined by mutation rate in the paper. So I select for those genes and only deal with these genes from now on. But I still have two separate tables, two separate files. So what I want to do with those genes is kind of explore them. The first thing I do is I look for outliers, which is defined as 3 standard deviations from the mean. When I find outliers, what I do is I initially set them in 99th percentile, but that was still outside the outlier range. So I just brought them back into the limit of the range. What was 3 standard deviations from the mean is what I set my outliers to. There were only upper outliers. There were not any lower outliers. So then I know I want to normalize my data. So what I do is I print out histograms. I observe them. I print out a histogram for each gene and a histogram of a log transform of each gene next to it. And as you can see, log transforming the gene really takes the skewed data and converts it to a normal distribution, which is exactly what we want. So that's what I did. I took the data and I did a log transform. I then did min-max normalization. I created a function, and as you can see, my data is now between 0 and 1. So now it's time to merge the tables. I had to do a little bit of string parsing and formatting, but I then did a inner join on the patient ID, and I have one table now. So now that I have one table, I can explore my data further. I looked at age. It has a normal distribution. It doesn't have any outliers. Great. Skip over that a little bit. I then look at correlation of the data. There's nothing really that stands out. Most of the data is not correlated. The higher values are like 2, 0.2, 0.3, which isn't significant, and there are a couple values that are like 0.7, but nothing that really concerns me. So that looks good. The next step is cleaning and shaping. I kind of already did that with the gene expression, but I'll continue it now that I have one table. I pretty much do imputation here, and I impute the categorical variables. And I pretty much use mode here, and I was comfortable doing it for every variable. There wasn't a major issue. There weren't that many missing values, and the modes were significant. So I continue doing that here. For this feature here, I set my this factor as ordinal. It's smoking status, so from non-smoker to heavy smoker, essentially. There's no missing data from this. This is the last numerical value. I had to do a log transform. Last thing I did with the data was I created dummy variables. All 3 of my models take numerical data, so I needed this. So now I'm ready to create my models. The first thing I did was I created a regression model, and to do that I needed only the numerical features, so I selected for those. I created a training and testing data sets. Here's the summary from my initial model. Let me run this. So there you can see. So that's a lot of features. So what I did was I did stepwise backwards elimination with AIC, and this output's very long, so I'm not going to run it. But I will show you the summary. You can already see it. So it did eliminate a lot of the features, and my accuracy was 0.71, which was good. That's pretty good. But one thing about this that I was concerned about was the p-values. Some of the p-values were high. So what I wanted to do is I did some manual stepwise backwards elimination with p-value. I did it about 13 times, and I reduced the features to 4. All of them were statistically significant. I raised the AIC a little bit, but I dropped the accuracy. So I went with the original model. I then created a neural net. I created a testing and training set. Started with one node in the hidden layer. There's only one hidden layer here, and got an accuracy of 0.6. It's not awful. It's not great. And then I kind of tune that with parameters. I tune the parameters. The accuracy keeps going lower. I add another hidden layer, and that does increase the accuracy, or it should. No, it doesn't. I apologize for leading you on. I then add another hidden layer. Let's see how this runs. Once I add hidden layers, there's variability in output. I ended up choosing this one as my final model because it had a range. It did have the highest output in terms of accuracy. It had about an 83% accuracy at one point, so I chose this one. Plus, this isn't very scientific, but I think it just looks really cool when you have hidden layers and nodes. So then I went and trained my support vector machine, and I started with a vanilla dot, which I'll run. This ended up being the best model in terms of training error and accuracy. The accuracy was 0.67. I tried all the other different kernels, and they were all not as good as the vanilla dot, so I kept the vanilla dot. So then what I do next is I do a k-fold cross-validation. I look at my kappa statistic. It's not bad for regression, but it's really bad for neural net and support vector network. It's 0.05 for neural network, which is just brutal. And then I compare my models with a more traditional method. I do a confusion matrices, which give me the accuracy, they give me the confidence interval, which is great, and it gives me sensitivity, specificity, kappa value. So again, we have 62%, 67. So then I look further at the AUC. I have it's not awful. It's a little bit bad on the support vector machine and the neural net, but it's not awful. So finally, I create a stacked ensemble model. First, I do a little bit of boosting. I use a method from the Adabag package, and on that model, I have 97% accuracy, but I am concerned with overfitting in this case. So then finally, in my stacked ensemble, I take the output, the predictions from the 3 previous models, I feed them into a majority vote algorithm that I created myself, and that kind of outputs a new vector of predictions, and that has an accuracy of 71%, so it's not bad. So a false prediction in this case it's not the drastic. There's no drastic implication. It's not the worst thing in the world. So 71% accuracy could be acceptable. It's yet to be concluded, but thank you for listening to me speak, and take care.